In the previous video, we learned about the working of a scan chain and how we generate test patterns with the help of a scan chain. We understood how patterns are generated for fault-free and faulty logic. We also learned how to determine whether a logic is faulty or fault-free just by observing the test pattern. I recommend watching the previous videos to understand this one fully. In this video, we are going to discuss ATPG and pattern simulation. Hello folks, this is Ankit and I am passionate about bridging the gap between technology and understanding. With background in DFT, I created this channel to help engineers, students and tech enthusiasts navigate the intricate world of DFT. I'll try to explain DFT, which is a crucial part of chip design, in the simplified way possible. I'll cover both theoretical and technical concepts, as well as discussed many problems and issues we face as DFT engineers, and I'll try to explain the solution in the most simplified way. So, what is ATPG? We have already learned about TPG from past videos. Now, what is TPG? TPG stands for Test Pattern Generation. ATPG stands for Automatic Test Pattern Generation. It is an automated process of generating test patterns. Earlier, we used to generate test patterns manually in the previous videos because circuits were very basic, such as OR gates and AND gates. However, in real-world scenarios, circuits are so complex that it is nearly impossible to generate patterns manually. So, we require a tool that generates patterns for us to test manufacturing defects in chips. These are commercial ATPG tools we primarily used as DFT engineers to generate test patterns. We have Tessent Test Compress, Synopsys Tetramax, and Cadence Modus. Now the question is, why is ATPG needed? Take the wafer process flow as an example. Starting from bare wafer, it goes through various processes such as wafer preparation, oxidation, diffusion, ion implantation, chemical vapor deposition, photolithography, metallization, and packaging. Defects generated in each step may be carried forward, accumulating throughout the process. Therefore, we must ensure that the products manufactured meet the quality requirements before proceeding to the next step of packaging and testing. In a nutshell, detecting faults is crucial to ensuring the quality of a chip, and we detect these faults using ATPG. Let's understand how ATPG helps us with a real-time scenario example. Before moving further, it is important to understand three terms. First is golden response. This is the response of a fault-free circuit when test patterns are applied to it. I hope you all remember from the video on the working of the scan chain that we generated a test pattern for a fault-free OR gate input. That test vector can be considered as the golden response for a fault-free OR gate input pin. Second term is actual response. This is the response of an actual physical chip when test patterns are applied. It can be the same as golden response or different. When the golden response matches the actual response, we say the chip is fault-free. However, if the golden response differs from the actual response, we say the chip is defective or fault-free. Third term is ATE, Automated Test Equipment, a crucial component in VLSI testing used to verify the functionality, performance, and reliability of semiconductor chips. It automates the process of testing integrated circuits and helps identify defects before mass production. This is an actual picture of a ATE, and let me tell you, it's a very expensive machine. Most chip making companies do not own their own ATEs. Instead, they use ATE from other companies to test chips and pay them on a time-based model. The longer a chip is spent on a ATE, the higher the cost of manufacturing company, ultimately making the chip more expensive for consumers. How to reduce this cost? DFT engineers insert a logic called EDT, that is embedded deterministic test, to reduce the test time of a chip. I'll explain EDT in detail in a separate video. Here is a diagram explaining what happens on ATE. With the help of ATPG, we generate patterns for a chip. After manufacturing, the chip is sent to ATE for testing along with the test vector files. On ATE, test patterns are applied to the physical chip and the actual response is recorded. The golden response provided by DFT engineers is also stored on ATE. A compare unit on ATE checks whether the golden response matches the actual response. If they match, the chip passes the test, meaning it has no manufacturing defects. If they differ, the chip fails the test due to manufacturing defects. Types of pattern files generated by ATPG. First is .v file, also called a test bench. After ATPG process is completed, we simulate these patterns to check their validity using a simulation tool. Second is STIL file. This format is sent to ATE for testing the physical manufactured chip. Third format is Wiggle file. This is also another format used for chip testing. The last is binary format. This can be considered as the golden response pattern, which helps in simulation debugging. Each pattern format has its specific purpose, which we will discuss in detail when we cover the ATPG flow in upcoming videos. After generating patterns through ATPG, the next step is to simulate them. So, the question arises, what is pattern simulation? Before understanding pattern simulation, we need to understand simulation itself. Simulation is the process of creating a virtual model of a real-world system to analyze its behavior under the different conditions. It helps in understanding, testing, and predicting the system performance without physically implementing it. For example, in the movie Iron Man, Tony Stark simulated his suit design before manufacturing it. Through simulation, he was able to analyze potential issues and rectify them before making the actual suit. Pattern simulation in design for testability is the process of verifying that ATPG generated test patterns correctly detect faults in a simulation environment before applying them to an actual silicon using ATE. It ensures that test patterns work correctly in simulation, they meet timing and DFT constraints, they detect faults effectively, false failures on real hardware are avoided. Why is pattern simulation important? Here is a list of reasons and their impacts. Read it carefully. Terms like fault coverage and yield loss will be discussed in upcoming videos. Tools used for ATPG simulation. The major ATPG simulation tools available in the market are VCS from Synopsys, Questa from Siemens, Xilium from Cadence. In a nutshell, pattern simulation is a critical step before applying ATPG patterns to real silicon. It ensures that test vectors function correctly, meet timing requirements, and detect faults as expected. Without simulation, expensive ATE time could be wasted on patterns that do not work properly. I hope you found this video helpful. Please share your feedback and valuable suggestions. Thank you.